Good morning, colleagues. First, I want to apologize for my voice. I got cold and I lost my voice. I'm the doctoral student of the Department of Measurements here at this faculty of Electrical Engineering at ČVUT. And today I would like to present some results of my research. But first, I would like to say a couple of words about the sensor, because nanocrystalline is used in different sensors, but for my research, I tested this in particular sensor, fluxgate sensor. And a couple of words about principle of work. So we have two symmetrical part of the sensor, but the direction of current is different in each direction of excitation current is different to make it can't cancel each other out without any external field. And when we have external field, there is a resulting shift of the of these sinusoids, and this result is like final sensitivity. And the most important part of this sensor is magnetic core, because like entire principle of work of this sensor is based on how good magnetic material will perform and how it will react on external magnetic field. And yeah, so that's why it was interesting to find some new type of material to improve the work of the sensor in terms of sensitivity, magnetic noise. And before we already did some experiments with permalloy, with amorphous wire, co-based amorphous alloy. And these materials are conventional, but like they give good results, but we could improve the work of the sensor, trying using another type of material, which is fine mat. It's nanocrystalline. And why it's good? Because it combines properties of two types of materials, crystalline, like permalloy types of material, and amorphous alloy. The best thing about this type of material is that we can process this like master alloy of this material in certain way to get a certain like state when we have like different sizes of domains or different ratio between amorphous state and crystalline state. And after a certain processing, we will get properties of this material which could be much better than, not much better, but it could be better than other types of alloys in terms of using it in fluxgate sensors. So it's like a couple of words about the experiment. What we cannot change is chemical composition, because this wire is ordered in Romanian Institute of Physics, and it's like a ready wire, S-cast alloy, and it has diameter 12 millimeters, or 120 micrometers of diameter, but while processing of this wire, we can change certain parameters like tension, applied stress, annealing temperature, duration of annealing, and some parameters like gas and etc. And also, while changing parameters of processing of annealing, we can change grain size, domain size, which is really important for changing, for getting optimum state of the material to get nice results. And ratio between amorphous and crystalline state and other. So So here are some pictures of like theoretical background. At the picture 7, you can see process of crystallization, because it's like a step-by-step process, and we need to anneal it till some point when until some temperature. When this process already started, because, for example, if it's too short, material still didn't crystallized because this grain growth is like it takes some time. And also, we shouldn't exceed some point of annealing because domains will be too big, and coercivity will be too high, and permeability will drop as well. So we have a flash annealing process, and it means we should do this really fast. So it's about our annealing process. It's a tube filled with argon gas to prevent oxidation, because we found out when annealing is done in oxygen, it could be oxidized. And coercivity could be much higher than as cast alloy. So we apply current to heat it up. And then we test it in a single type of fluxgate sensor just to build a BH loop and characterize our material. So some of results of characterization. Picture number 13 is kind of picture what you would see in a lot of literature, but we tested again and have seen that yes, this material is exactly like theoretical. So with applying higher stress tension, and this stress tension is used to relieve some stress inside of material after processing it, because during manufacturing process it could have some some stress. And when we apply higher tension, we could get lower coercivity, like minimum coercivity is much lower than like minimum coercivity for the cases when applied stress is a bit higher or a bit lower. But permeability is not high, and so we need to find this optimum point when applied stress is enough to decrease the coercivity and still keep permeability high. So here is comparison of results of fine mat wire with amorphous, co-based amorphous wire. And in terms of sensitivity, it is plus minus the same, because you could see at figure number 15, red color is stands for co-based amorphous, and you could see that sensitivity is just a bit lower, but it looks like here is spike, and even if you will slightly increase the excitation, it will drop much rapidly than it is for nanocrystalline wire. So much like the characteristic for nanocrystalline core is much flatter, which is better. And in terms of noise, if you would compare noise at the maximum of sensitivity, we apply certain excitation for getting a maximum of sensitivity and measure noise. For amorphous, it will be a bit better situation. But when we change excitation, when we increase it, for a fine mat, it is possible to reach much lower magnetic noise and still get like very similar sensitivity than for amorphous. So after this, like the goal of getting like at least a bit better magnetic materials than co-based amorphous is reached, because before it was like a stereotype that co-based amorphous magnetic material is better than fine mat. But at least we can show that it is not better. It could be the same or worse than fine matte. So we are going in the right direction. And here are some results of magnetic characterization of material. And we could, so here is comparison of different results of annealing under different conditions, under different current, and when we apply different current, it's different temperature and different stress. So you could see that after some point of applying stress, permeability is like increasing and then decreasing, and then for temperature it looks similar, but a bit characteristic is a bit flatter. So temperature, like stress, applied stress is really important, and also results of measurements. Like sensitivity and noise, and how different annealing conditions impact on these two characteristics of sensors. And time of annealing is also important, because after some, even if we keep some certain stress and current, I mean temperature, still this time of annealing, after exceeding some time, coercivity rockets. So, yeah, but yeah. So let's. Here is a comparison of two sensors with two different types of cores. One core is annealed with with current to 497, but stress tension is like 12 megapascal, which is weight 14 grams. And another type of wire has the same conditions, but weight is twice higher. It's 24 megapascal, which is 28 grams. And what we could say that this change of stress is quite dramatic, because sensitivity is almost twice higher for the wire with lower stress. But for the results, when we apply even lower stress, it goes like results are worse. I can show you previous graphics when stress was lower than 14 grams, 12 megapascal. So it's kind of optimum point where optimum point for this certain wire when applied stress is 12 megapascal. And this current is also optimum current, 497 milliamps. But this characteristic is more flatter for wire with higher tension, which could be used in some sensors where stability is more important than sensitivity. So conclusions, this sensor based on fine matte wire is quite nice, and it shows better characteristics than amorphous. Not much better, but still it is better, and we should continue working on it to get even better results. So thank you for your attention.
Thank you, Diana, for your presentation. And as usual, we have some time for, let's say, one question. Yeah.
Thank you. Can I ask you, go back to the graphs? I think 3 slides back. Another one? Here, okay. If you look top left the graph, there is a very sharp change of the trend. There are 3 points up there, and then it goes rapidly down. Do you know what can be background of this effect? Is it caused by the material property, or by the process, or by the measurement setup?
I guess it was caused by the rapid growth of grain sizes. And I guess when we apply this type of like tension, it prevents domains growing because of tension, and there is some certain point when we have like I will show you this theoretical graph when there is like yeah, for example, this Hrakova diagram, where is in this part there is some small part, but you can see that the growth of coercivity is really dramatic. This is like in this short grain size, and I believe that in like previous graph, or even after like increasing the tension for like some not high tension increase, still this this coercivity and like coercivity goes up rapidly, and magnetic permeability goes down, and because there is some certain point when the grain size is too like it has some certain size which is not optimal.
Okay.
Okay, and since there is no more time for another question, thank you again, Diana.